and you can go.
Okay, so I did my project over vector fields. And so a vector field is where a bunch of vectors are plotted to create a field of vectors allowing for the observation of flow. A vector field uses vector calculus as a base to allow calculations of these types of flows. This can either be 2D or in a 3D space. Common uses of a vector field is in determining the speed and direction in which a fluid flows. Uh, and the reason why I chose this is because I'm trying to become a petroleum engineer, and they use this type of math to determine flow of oil or gas through pipelines. So a basic formula for work on a particular flow point is the vector field f of x of y is equal to a scalar vector of xy plus another scalar vector of xy to the vector of j. And to define the path of which the particle flows through, you get position vector r to the t, which is equal to x to the t plus y to the t, and you get a is less than greater than t, and then t is less than greater than b, which is the 2 points it's between a and b. And so the formula for the work done on the particle is the derivative of vector field f times, or the integral of vector field f times the derivative of the position vector, which, and then the derivative of the position vector is x prime t dt plus y prime t dt. And so the final formula you get is the first scalar vector times x prime plus the second scalar vector times y prime. And so to sort of put that all into a formula, so for example, our constants for x is cosine t, and for a constant y, it's sine t, and it's between 0 and 2 pi. So when we go and start plugging that stuff in, so we start off with our formula of vector field xy is equal to y minus x, and then the path formula for it would be cosine t plus sine t. And the derivative of that would be negative sine t dt plus cosine t dt. And so then we multiply the vector field times the path vector, which you see there, and then you get your final equation of 0 to 2, with the limits of 0 to 2 pi, um, sine squared plus cosine squared dt is equal to you take out the negative and put out in front, which is from limits 0 to 1 dt, because so sine squared plus cosine squared cancels out into just the 1 with the with our formulas that we've learned throughout the school year. And so once you get the antiderivative of 1, you get a negative t from 0 to 2 pi, which then you just plug in. And so you get negative 2 pi as your work done. And since it's a negative, that means there's negative work being done, which means the particle is slowing down throughout the vector field. And so who invented vector fields? Vector calculus and its subjective vector fields was invented by two men, J. Willard Gibbs and Oliver Heaviside, at the end of the 19th century. This allowed scientists and mathematicians to calculate such things as speed and direction from a graph. It also allows for greater visualization of what is happening with these types of numbers. And those are the two men there at the bottom. And some graphical examples of vector fields is the polarization of Earth's magnetic field, which is on the left here. And then in the top center is the airflow over a wing, airplane wing. And then you can also use it for weather, like the weatherman graphs and whatnot, of airflow of high and low pressure, which is the top right there. And so in conclusion, prior to researching about vector fields, I didn't really know too much about it and how it pertained to calculus until I started researching all this. And I've always I've always seen vector fields before, but I didn't know what they were used for. And so it amazed me of how much you can derive from just a simple graph of pointing lines, really, of like speed and flow and whatnot. So, and that's my work side, and that's it.